In this last section of Chapter 2, and Chapter 2 is on rules for calculating derivatives, the topic in the section isn't the kind of thing it's been for the last few sections, which is here are some specific functions and here are their derivatives. The topic in this section is harder to talk about without getting very, very technical. It's on implicitly defined functions. So it'll be easiest to do this with 3 examples. You can read the details in the book. It's easy to understand the kind of general gist of what's going on. It's harder if you want to understand the technical, much harder if you want to understand the technical details or even the definitions. So what's a typical easy problem? Well, an implicitly defined function. Suppose you're supposed to find the derivative the derivative dy dx, where, say, x squared minus y equals 7. What's different about this question? Not much. I mean, you could solve this for y, and you get that, put the y over here and the 7 over there, but I like writing the y first. So you get y equals x squared minus 7. And then you differentiate it, and you get 2x. What's different about this? What's different is we're not given y as a function of x to start with. It's close, but what we're really given is here's some function of x and y, and here's some other function of x and y. It happens to be the constant function 7. But you've got some function of x and y equals some function of x and y, and you're supposed to just assume that somehow that defines y as a function of x for you. In this example, it's incredibly easy because you can explicitly solve for y and then calculate that dy dx equals 2x. No problem. Okay, but what if you had something more complicated? So suppose, so this is the first serious example. Suppose x squared plus y squared equals 1. Find dy dx. Okay. This is not quite as easy. It's not too bad, but it's not quite as easy. It's, okay, you're given this function of x and y equals a constant, so it could be any other function of x and y, but it's a constant again. For that matter, if you had a function of x and y equals a function of x and y, you could always subtract one side from the other and have some function of x and y equals 0. So you've got this function of x and y equals a constant, and you're told to find dy dx. What you're assuming is that this equation implicitly defines y as a function of x. Implicit as opposed to explicit. Explicitly defining y as a function of x means here's y, and it equals this in terms of x. Implicit, you're given some relation satisfied between x and y, and you're just supposed to assume that somehow that tells you what y is as a function of x. That's not quite true, but we're going to look at that in this example. Implicitly defines y as a function of x. That is not quite true, and we're going to have to look at to what extent that's not quite true. But what you can do is solve this, try to solve this for y as a function of x. So you subtract x squared from both sides, and you get y squared equals 1 minus x squared. And then you take square roots, but this means that y could be plus or minus the square root of 1 minus x squared. And this is why this equation doesn't define y as a function of x. Y could be plus or minus this. A function, if y is a function of x, when you give one x value that's in the domain, you're supposed to get back exactly one y value, not a choice of two different y values. If you graph this, you should know what the graph of x squared plus y squared equals 1 looks like. If you graph this, what you get is a circle of radius 1 centered at the origin, so the unit circle. So here's the graph of x squared plus y squared equals 1. Graphically, how do you see that this is not the graph of a function? Well, to be the graph of a function, if you're given an x value in the domain, so some x value that you get, you're supposed to have one y value. But that means that the graph of a function should satisfy a vertical line test, because this means you fix an x value and there should be at most one corresponding y value. At most, because if there were no corresponding y, that's an x value not in the domain. But if we're given x here, there are two corresponding y's, so there are vertical lines here. There are some vertical lines that intersect the graph more than once. That means this is not the graph of a function, because that exactly says for that x value, there's more than one given y value. And we get plus or minus. So we get that y could either be plus, so it could be 1 minus x squared, the square root of 1 minus x squared, or y could be negative, the square root of 1 minus x squared. In this example, what we're getting for y clearly breaks up into two functions. One that describes the y's that are greater than or equal to 0, so that would be the top half of this circle. So the upper half circle. So that's this one. Or this one is where all the y coordinates are 0 or negative. So that's the lower half circle. These two half circles intersect where y equals 0. So if you knew whether y was positive or negative, then it would tell you which one of these functions you're talking about. If you're told that y is 0 or y is close to 0, it's completely unclear. If you just knew that you were near where y is 0, well then part of the graph near there would be on the upper half and part would be on the lower half. So what does it mean to find dy dx? Well, if you were told that y is positive, then you would take dy dx of this one and calculate the corresponding derivative. If you were told that y is negative, you'd calculate the derivative of this. The only problem is where y is 0. So the question is, can we could do those two separate problems. Get one thing when y is positive, get something else when y is negative, and say that the derivative is one of those, depending on whether y is positive or y is negative. And I am going to do that. The real question, though, is can we somehow calculate what dy dx is without explicitly making the choice first of y needs to be positive, y needs to be negative. After all, if we put a fairly complicated function of x and y in here, instead of x squared plus y squared equals 1, we could easily have no hope of solving algebraically for y in terms of x, and yet still wonder if we could calculate dy dx, wonder if somehow that equation implicitly still defines y as a function of x. But let's do this problem right now. So we're looking at x squared plus y squared equals 1, and assuming that implicitly defines y as a function of x. As we've seen, if y is positive, we know what function we've got. If y is negative, we know what function we've got. If y is allowed to be 0, or we don't know whether it's positive or negative, well, then we don't know what function we've got. So we started with this. Let's look at two cases. So there's case 1. We know that y is greater than 0. Then we know that y is the square root of 1 minus x squared, which is 1 minus x squared to the 1/2 power. And then we calculate the derivative of this. That's not hard to do. dy dx equals, it's the chain rule. You have one function of x on the inside, 1 minus x squared. The outside function is raising to the 1/2 power. The chain rule tells you the derivative. You differentiate the outside function, so raising to the 1/2 power. That's the power rule. The half comes down, you subtract 1 from the exponent. You get this, you leave the inside function exactly how it was. But by the chain rule, you have to multiply times the derivative of the inside function. And so you get an extra minus 2x. If you simplify this, the 2 cancels with the 2. You're left with a minus x, and then times a 1 minus x squared to the minus 1/2. That's 1 over 1 minus x squared to the positive 1/2. So 1 over the square root of 1 minus x squared with a negative x in the exponent. So you get negative x over the square root of 1 minus x squared. What's nice is to rewrite this as, we start with y equals the square root of 1 minus x squared. We end up with the square root of 1 minus x squared in the denominator. So what you can write is that what you end up with is minus x over y, which is nice looking. It's a nice looking formula. It looks nicer than that. What about case 2? In case 2, we're looking at where y is less than 0. And when that's true, we know that y has to be, and assuming x squared plus y squared is still 1, we get this. So this is negative 1 minus x squared to the 1/2. And what's the derivative of this? Well, it's just negative what we got a minute ago. So it's just x over the square root of 1 minus x squared. You just differentiate this the way we did a minute ago, and you'll get this, negative what we got before in terms of x. But if you look at this, this is negative x over negative the square root of 1 minus x squared. Why write it like that? Oh, because the negative square root of 1 minus x squared in the denominator is exactly y again. So you get, the formula you get is negative x over y. So what? What are we seeing? We're seeing that, okay, yeah, if you're given this, it doesn't define y as a function of x. It kind of implicitly defines y as a function of x if you know y is positive, or it implicitly defines y as a function of x if you know y is negative. And in either one of those two cases, when you differentiate with respect to x, you can write one formula that gives you the derivative in either case. Yes, you can write it in terms of just x and get here minus x over the square root of 1 minus x squared, and here positive x over the square root of 1 minus x squared. But if you write the answer in terms of x and y, you get the same formula in both cases. You get minus x over y and minus x over y. So great. And that formula, the reason it's conceivable that you have one formula is that having y in your answer means that what you're actually getting for an answer can depend on whether y is positive or whether y is negative. So what are we getting for the answer? We're getting minus x over y, as long as y isn't 0, which is also the only place where the derivative has a problem when you're dividing by y equals 0, which was kind of the overlapping case that we had to leave out anyway. We could handle where y is positive, we could handle where y is negative, but we didn't know whether we had the plus or minus if we were close to where y is 0. So what we're finding is dy dx equals minus x over y if y is not 0. The question is, could we have gotten this one nice formula without breaking things up into cases? And the answer is yes, you can. And it's almost like magic. It's really very cool. You look at this equation and you assume that y is some function of x that makes it true. So assume y equals y of x is a function which satisfies this equation for all x in some open interval, so that we can take derivatives for all x in some open interval. Okay. Well, what happens if you do that? Well, if we assume that y is some function of x that makes this true, what do we mean makes it true? Well, we mean that we get an equality of functions. This side will be some function of x. That side is a function of x. It's a very stupid function, or a very simple function. It's constant. So in ordinary English, you wouldn't say it's a function of x because it doesn't depend on what x is. But in math, we still say it's a function of x. It's just a constant function. So if you assume that y is a function of x which satisfies this for all x in some open interval, then this side's a function of x, that side's a function of x, and we're saying these two functions are equal for all values of x in some interval. So, of course, in this example, we know what those functions could be. Either y is positive and y is this function of x, or y is negative and y is this function of x. And yes, it's true, if you take x squared and add this squared, you get 1, so that this equation is true. Or if y is negative the square root of 1 minus x squared, if you put that in here, this equality is true. Who cares? What am I talking about? Of course, how does this do you any good? You can apply the chain rule. You can differentiate both sides of this equation with respect to x, just assuming that we know y is a function of x. What happens if you do that? So you differentiate both sides of the, let me move to the other board. So you differentiate both sides of this equation with respect to x, keeping in mind that you're assuming that y is a function of x. There's a big theorem going on here that says basically whatever you find for the derivative this way, wherever it's defined, your assumption that y was a function of x there is correct. It's called the implicit function theorem. So we have x squared plus y squared equals 1. And we want to just assume y is some function of x for x in some open interval. Then you differentiate both sides with respect to x. So you take d dx of both sides of the equation, keeping in mind that y is some function of x. That we're pretending right now we don't know what y is. Of course, in this problem we do. It's plus or minus the square root of 1 minus x squared. But in harder problems, and we'll do one in a minute, you wouldn't be able to solve for y. You wouldn't know what y is in terms of x, and yet you can still do the kind of thing we're doing now. So you take derivatives, both sides, with respect to x. Well, this side is certainly easy. The derivative of a constant is 0. What about this side? The derivative with respect to x of x squared, 2x. Then there's, now you have to be careful, the derivative of y squared, but with respect to x. If we were differentiating with respect to y, you just get 2y. But we're not. Y is some function of x, and then we've squared it. We need the chain rule. Here's one function of x, y, and then we've done another function of that. We've squared it. How do you differentiate that? You differentiate the outside function, squaring. So you bring the 2 down. You leave the inside stuff exactly how it was, so sitting there as being y. And then the exponent drops 1, so you just end up with y to the 1. But by the chain rule, you have to multiply times the derivative of the function inside with respect to x. The function inside is y. We're differentiating with respect to x, so you get this. And you might say to yourself, but I don't know dy dx. That's what I'm trying to find. Exactly. We need to get this dy dx in the formula because we're trying to solve for dy dx without ever explicitly solving for y, which is what makes this so cool. You can now solve this for dy dx. You divide by 2, divide both sides by 2, put the x over here and divide by y, and what do you get? You get dy dx equals negative x over y. you get the formula that we got before by explicitly solving for y as a function of x in two different cases, and then differentiating and seeing that, if we replace this expression with y everywhere, we get this. But if we just assume y is a function of x and differentiate both sides of the equation with respect to x, making sure we use the chain rule, you produce some dy dx's, you solve for dy dx, and you get the correct answer. And the theorem, the implicit function theorem, is this is fine. That's a very loose statement of the implicit function theorem. But it basically says that for all the functions we deal with, for elementary functions, but now in terms of x and y, that this process is fine, and whatever you get for dy dx, if it's defined, then this was a correct way to solve, and in fact, y, it is okay to assume y is a function of x for all the x values, near all the x and y values where your function is defined. So we need to avoid where y is 0 here, but near places where y is not 0, y is a function of x, as we saw before, and this will be the derivative. Okay, let's do a harder example, which might make things more clear. This example is easy enough and we can kind of solve that you might not see the real point. So let's do something just kind of not horrifically difficult, but not too easy. One where we have no hope of solving algebraically for y in terms of x, even with a plus or minus sign. So a typical problem, typical instructions might be, there's a particular example I want, something like, so another example. Suppose y is implicitly defined as a function of x by, and I want y minus x equals e to the xy. Find dy dx. Where, how about when the pair xy is -1, 0? This is kind of standard when you're finding derivatives of implicitly defined functions. I didn't just specify find the derivative when x is this, but when x is this and y is this. That's pretty much necessary because it's like in our example with the circle. The x-coordinate doesn't tell you what the corresponding y-coordinate is. With the circle, for instance, if you picked an x-coordinate, y could have been plus or minus something. How do we know which one we've got? Well, in that example, I said, oh, well, and we're told y is positive or y is negative. But more generally, if you're given an x here, it's impossible to algebraically compute y. Some calculators can estimate it, but we can't solve this for y in terms of x. And so if somebody hands you an x, there's no way in practice for you to produce a y. So and there's no reason to expect that there's only one y. So if someone wants you to calculate the derivative, they have to tell you an x and a y value. One thing you should do, just because it would save you some time and and it could help you avoid having to do a problem at some point, you need to make certain that this point xy actually satisfies the equation. If it doesn't, then there's a mistake in the problem. And you just shouldn't go on because you're supposed to be finding this derivative at some point that actually satisfies this equation. So you should verify, or we should verify, that if you take, so there's the y-coordinate, there's the x-coordinate, we need for 0 minus -1 to equal e to the -1 times 0. If this isn't true, you might as well stop the problem because something's wrong with the way it's phrased. There's a typo or a choco or whatever. So 0 minus 1, that's plus 1. This is e to the 0, that's plus 1. Ah, too bad. We actually have to do the problem. Okay, so this is a point that satisfies this equation. Can we find dy dx? Sure. And in fact, it's not particularly difficult. Although, there is some chain rule, and then you have to do some algebra to solve for dy dx, but the algebra is never really bad. So we've got y minus x equals e to the xy. You are supposed to assume that y is some function of x that we don't know. We don't even have a plus or minus this time. But assume y is some function of x that makes this equality true for all x's in some interval, so that we can take, so that this is an equality of functions of x, and we can take derivatives of both sides with respect to x and still get an equality. So you do that, and you just keep in mind y is some function of x that we don't know. So you take the derivative with respect to x of both sides. All right. So what do you get? The derivative with respect to x of y. Well, that's dy dx. It's the thing we're trying to find. So you get dy dx. There's nothing else you can write. It's just that. Minus the derivative of x with respect to x. Well, that's just minus 1 equals. And then the derivative of this with respect to x. This is e to some function of x, because y is a function of x is a function of x, so x times y is some function of x. This is e raised to some function of x. The derivative, you use the chain rule. The derivative of e to the x is e to the x. Chain rule tells you the derivative of e to the anything. You get the e to the anything back, but then by the chain rule you have to multiply times the derivative of the anything. So the derivative of e to the xy with respect to x, you get the e to the xy back, but then you have to multiply times the derivative of the exponent, but derivative with respect to x. So this. But then you calculate this. This is y is a function of x, so this is the product of two functions of x. To calculate the derivative, you use the product rule. It's the first thing times the derivative of the second. But you have to remember, you're not taking the derivative of y with respect to y. You're taking derivatives with respect to x everywhere. So when I say the first thing times the derivative of the second, I mean with respect to x. First thing times the derivative of the second, so you get another dy dx, plus the second thing, the y, times the derivative of x with respect to x. But that's 1 again. So you get this. You get dy dx minus 1 equals e to the xy times x dy dx plus y. And we want to find dy dx. Now it's an algebra problem. You've got dy dx on both sides of the equation. You want to solve for dy dx. What do? You multiply out this side. You collect the terms with dy dx on one side, put the other terms on the other side. You factor out the dy dx and you divide. So I said that quickly, but that's what we're going to do. So you get dy dx minus 1 equals, you multiply this out because we want to collect dy dx terms. So if you multiply this through, you get x e to the xy times dy dx plus, so when I say multiply it out, you distribute multiplication over addition, plus y e to the xy. Okay. So you get that. What do you do now? Either you put this term over there and put the 1 over here and factor out the dy dx, or you could put the y e to the xy over there and put this dy dx over here. It doesn't matter. So you just do one of those or the other. I'll just pick one. I don't want to leave that there. So what do you get? You get dy dx minus x e to the xy times dy dx equals 1 plus y e to the xy. This. Oh my God, what do you do now? You factor out the dy dx over here and you divide. So you get dy dx times 1 minus e to the xy equals 1 plus y e to the xy. And now you divide both sides of the equation by this. And so you get dy dx. You get our general formula for the derivative. Dy dx equals 1 plus y e to the xy over 1 minus x e to the xy. This is kind of standard for how derivatives obtained from implicitly defined functions look. It's some quotient of, I don't know, fairly complicated looking functions in terms of x and y. They almost always come out like this. The only difference is how complicated the functions are. Like before we had minus x over y. That looks a little nicer than this. But this is not terribly difficult. And so you get this formula. When is it good? Whenever this, because we had elementary functions involved, whenever this derivative is defined, then that means that near that x and y coordinate, then it was correct to say that the original equation tells us that y is some function of x near there. It's not some nice function that we've got a name for. It's not some elementary function, that we can name. Maybe it's an elementary function, but it certainly doesn't look like it. I doubt that it is. Actually, I'm sure it's not. But there's a theorem that tells you that, yes, in fact, it was correct to assume that y was a function of x at least near the given x and y coordinates. So for instance, if this quotient is defined at minus 1, 0, then in fact, there is a function y that's defined in an interval around -1 whose value at -1 is 0 and that satisfies this equation. In fact, there's only one. And its derivative really, the derivative of that function really is given by this. So, it's a theorem. But what do you do? What this means in practice is you calculate the derivative the way we just did, and it gives you the right thing if when you plug this in, you get something defined. So you do that. What's dy dx when x is -1 and y is 0? You take this and you plug in x is -1 and y is 0. So what do you get? Let me get this out of the way. I think I can fit it in right here. If x is -1 and y is 0, then in the numerator you get 1 plus y is 0, so this whole part is 0, 1 plus 0, over, in the denominator you'll get 1 minus x is -1, and then there's times e to the 0, but that's times a 1, so we get 1 over 1 plus 1, you get a half. So that's the derivative of y with respect to x at a half. What does that mean? It means yes. If you assume that this defines y as a function of x near the point -1, 0, which does satisfy this equation, then dy dx there is plus a half. If you wanted to see this graphically, what could you do? Well, a lot of calculators, and certainly computer programs, can graph things that aren't functions. They can graph implicitly, or they can graph these one function of x and y equals another function of x and y. So for instance, Mathematica, Maple, MATLAB, they can all graph this. And if you looked at the graph of this, you would see that the point -1, 0 is on the graph. And if you look at the slope of a tangent line there, you'll see that the slope is a half. Anyway, this is how you differentiate, well, first of all, what it means for a function to be implicitly defined, and how you differentiate functions that are implicitly defined. It gives us more functions to deal with, functions that don't have names, functions that we don't have nice expressions for, and yet satisfy reasonable formulas, reasonable equations. and it tells us how to differentiate them. It's a cool thing because you get a whole bunch of new functions defined in terms of kind of complicated expressions in terms of old functions. And you calculate the derivatives relatively easily. And in fact, the derivative formulas can be nicer than what you would calculate if you did find y explicitly, like we did for the circle, when x squared plus y squared equals 1. We don't want to break that up into cases. It's just so much nicer to find the derivative of y with respect to x implicitly. We will not use implicit differentiation a lot, but it's certainly nice when it comes up, and it's nice to know that you, or interesting to know that you have this additional way of defining functions of x without ever explicitly writing the function as in terms of our elementary functions, and maybe it's not even an elementary function. Okay, this is the last of our techniques for finding derivatives of functions. In the next chapter of the book, we will look at some additional applications. Of course, we've looked at applications of differentiation along the way, but now we'll look at some specific groups of applications that come up.